Welcome back to Learning as a Hobby, everybody. Today I'm going to continue with Michael Spivak's Calculus, fourth edition. I'm going to go through some of the exercises for part one, chapter two today. The reason I say part of them is because there's a bunch of problems here that to do, and they each are kind of long. So I think what I'm gonna end up having to do is break this up into two videos, just so that the video's not like 5 hours long or something. So in addition to the problems that he suggests to do in the book, which are let me see what questions here are again. 7, 8, 10, 11, 17, 20, 22, 23. In addition to those, I'm going to do some other problems along with those as well. One reason is because he refers to actually some problems back in chapter one that we didn't do on video. So I'll do those since he's referring back to those. And there's a couple other problems that I wanted to do in chapter two exercises that refer to important theorems that we might need for later on. So I might as well, even though he doesn't recommend doing those problems in the book, it might be good to just get them out of the way. This way, later on down the line, we don't have to prove them in later videos. I could just refer back to this one or the next ones. Like I said, I think I'm going to break it up into two parts. So I think what I'll do is I'll start with the chapter one problems, and then we'll do a few of the problems. Well, I guess I'll just do them in order. A few of the problems from chapter two, and then I'll leave the rest of them for the next video. So it should be two videos of maybe like an hour each. Hopefully, we'll see how it goes. Just because I thought the last exercise video was going to be like 45 minutes, and it ended up being an hour and a half. So I don't know. We'll see. So I'm going to start with the chapter one problems. And then I think what I'll do, I'm going to post this video, and I want to kind of get started on Schifrin's book. So I think before I post part two for the exercises here, I think I might move on just in the interim. I'll go over my notes for Schifrin's chapter one, and then we'll finish up in part two the exercises for chapter two here, and then I'll post a video with the solutions to the certain exercises in Schifrin's book. Okay, so hopefully I haven't confused everybody now, or maybe you don't even give a crap, but all right, anyway, let's go through the problems here. So I'm going to start like I said, in chapter one. I'm going to do we'll start with problem 1.7. So just bear with me while I write the problem on the whiteboard. I'm going to have to copy them down from the textbook here. So just bear with me. All right, so this is chapter one, problem number 7. And I guess I'll tell you the reason why I'm doing this one. A generalization of this. So a generalization of this result occurs in problem in exercise. What was it? 2222. All right, so let me write down the result that they want us to prove. So here is the statement. So prove that if zero is less than A, less than B, then A is less than square root AB is less than A plus B over 2, is less than b. Okay. He has a note here. It says also, notice that the inequality square root AB less than or equal to a plus b over 2 holds for all AB greater than or equal to 0. And then he says, generalization, this occurs in problem 222. So that's the statement that we want to prove, right? So let's actually do that right now. Okay, well, maybe I'll do this in parts. If A, so let A, whoops, 0 less than A less than B. Okay. Then square root of A, square root of B is are real numbers, right? They're positive real numbers. Consider square root of B minus square root of A squared, right? That's positive because the square, greater than or equal to 0. Or actually, it's strictly positive if B is greater than A. So actually, I don't need the equals. That follows from the fact that the square of every real number is positive. I think we proved that in earlier sections, if my memory serves me. I think we proved that. So squares are always positive of real numbers anyway. So this is always positive. And if I multiply this out using the distributive law, we get B plus A minus 2 square root A square root B greater than 0. That's the same thing as B plus A greater than 2. Square root A square root B is actually the same thing as square root AB by properties of exponents. Okay, and then divide by 2. Okay, so that proves the middle part, and the other parts follow from, can I fit this in the bottom line? Let me try. We know that A is greater than 0, right? Which means that A is equal to its own absolute value from the definition of absolute value, which is the same thing as square root of A squared. And that's less than square root A square root B because A is less than B. And we already just proved that this is less than B plus A over 2. And this is less than B plus B over 2, which is the same thing as B. All right, that proves the triple inequality. All right, that's 1.7. The next one that they refer to is, what is it, 118, I think. There's a lot of pieces to this one. So again, you're just gonna have to bear with me while I write all the parts down. 118, here we go. All right, part A says, suppose that B squared minus 4C is greater than or equal to 0. Show that the numbers negative b plus or minus square root 8 b squared minus 4c over 2. Both satisfy the equation x squared plus bx plus c equals 0. Okay, so I'm not actually going to prove this one because I'm assuming that if you're watching these videos, you've taken high school algebra already and you recognize this formula. What you do is you just plug those numbers in for x in the equation. So in other words, you take negative b plus or minus square root b squared minus 4c over 2 squared plus b times minus b plus or minus square root b squared minus 4c over 2 plus c. And you simplify that and show, so simplify and you'll see that you get 0. So I'm not going to bother with that just because it's just an exercise in algebra, and I don't want to waste time on something that is so straightforward. So that's part A. So I'm just going to skip doing that. Part B says, suppose that b squared minus 4c is less than 0. And they want us to show that there are no numbers x satisfying the equation Okay, in fact, that polynomial is always 0, greater than 0. So in fact, x squared All right, so to do this, he actually gives a hint here. He says just complete the square. So that's what we'll do. This one is also something you probably would have done in a high school algebra class, but I'll do it again here just because sometimes people, if you haven't taken a math class in a while, you might have forgotten how to complete the square. So I'll do that here. Or I should say, assume b squared minus 4c less than 0, and consider x squared plus bx plus c. Okay, if I complete the square, I get this. And now this is a perfect square by construction. So that's equal to x plus b over 2 squared plus 4c minus b squared over 4, right? And this quantity is positive, right? Because b squared minus 4c is negative. So that means this is always greater than 0. Okay, therefore there are no solutions that make this polynomial equal to 0, which means it's always positive. So that shows the statement is true. Right, part C. Use this fact to give another proof that if x and y are not both 0, then x squared plus xy plus y squared is greater than 0. Okay, proof. So start with the hypothesis, use this fact to give another proof. So assume that x, y are not both 0. Maybe we could say assume y not 0. We could do that without loss of generality. Then consider b squared minus 4c, where b is equal to y, c is equal to y squared. Right, then b squared minus 4ac, I'm sorry, minus 4c rather, is equal to y squared minus 3y squared. Oh, sorry, minus 4y squared, which is minus 3y squared. Okay, and because the square of a non-zero real number is always positive, and we're multiplying a positive by a negative, this is negative. So that means that the polynomial is always greater than or equal to 0 by, always strictly greater than 0 by part 2. So therefore, or was it part B, therefore x squared plus xy plus y squared is greater than 0 by part 2, or part B rather. All right, next page, part D. For which numbers alpha that's the Greek letter alpha. For which numbers alpha is it true that x squared plus alpha xy plus y squared greater than 0 whenever x and y are not both 0. Right, so similar type of reasoning. So B then will be alpha y, C will be y squared, and the condition is that B squared minus 4C has to be negative. So in other words, alpha squared y squared minus 4y squared, which is the same thing as alpha squared minus 4y squared. This has to be less than 0. And if y squared is not 0, that means that alpha squared minus 4 has to be less than 0, right? Which means that alpha has to be in the interval from -2 to 2. All right, so that's the solution for part D. There's a few ways you can solve that inequality. If you forgot in your algebra, if you just graph this polynomial, let's say this is the alpha axis, then the polynomial looks like this, where this is -2, this is 2. Notice that for alpha between -2 and 2, the values of the polynomial are negative. All right, so that's part D. Part C, I'm sorry, part E rather. Part E says find the smallest possible value of x squared plus bx plus c. And whoops, a x squared plus bx plus c, given that a is greater than 0, for a greater than 0. Right, this is relatively straightforward too. Again, you're just going to complete the square. Sorry, this isn't a proof, I'm just answering the question. So for the first part, we complete the square. Actually, we already completed the square on this before. So if you remember, we ended up with x plus b over 2 squared plus b squared. Sorry, plus c 4c minus b squared over 4. Right, so the smallest this can be is when x is equal to -b over 2. So this always has to be strictly greater than 4c minus b squared over 4. So that's the smallest value. Right, and similar type of thing for ax squared plus bx plus c. So I'll complete the square on this again, just in case people have forgotten how to do it. This is factor out an a to start with. So this is a times x squared plus b over a x plus b squared over 4a squared minus b squared over 4a plus c, right, which is the same thing as a times x plus b over 2a squared plus 4ac minus b squared over 4a. This is always greater than 4ac minus b squared over 4a. So that's the minimum. All right, so that's the answer for question 18 in chapter 1. One more problem left in chapter 1 to do, which is, what is it, number 19. There's a bunch of parts to this one too, so you can start to see why I'm gonna have to split this up into a few videos. So we're gonna do 119 next. Right, because he refers to this in later problems in chapter 2 that we're going to do. Maybe there's a lot of writing here. Maybe I should just read it out to you, I guess, and then I'll write the actual problems. So yeah, let me do that. All right, so in question number 19, there's a paragraph before the part A. From A, he says, the fact that a squared is greater than or equal to 0 for all numbers a, elementary as it may seem, is nevertheless the fundamental idea upon which most important inequalities are ultimately based. The great granddaddy of all inequalities is the Schwarz inequality, which I'll write so we have it as a reference. This is the Schwarz inequality. Whoops, there's no T. Schwarz, or sometimes called the Cauchy-Schwarz inequality. Or maybe that's a slightly more general formalization. Inequality. Okay, the Schwarz inequality says x1, y1 plus x2, y2 is less than or equal square root x1 squared plus x2 squared, y1 squared plus y2 squared. All right, that's the Schwarz inequality. I'll put it in a box. Okay, and then, so he says here in a note, a more general form occurs in problem 221. So that's the problem that we're going to need this result for. So this, a more general result. Actually, there's a few problems, I think, in chapter 2 that will appeal to this. A more general result appears in, what do you say, 221? And then, okay, so, and then after that, he says, the three proofs of the Schwarz inequality outlined below have only one thing in common: their reliance on the fact that a squared is greater than or equal to 0 for all a. So I'll just write that on the side here. So the important fact that these next three proofs of the Schwarz inequality that we're going to go through rely on the fact that a squared is greater than or equal to 0 for all a. Okay, so let's go through the proofs. Maybe I'll start part A on the next page. So let me write it out. So prove that if prove that if x1 equals lambda y1 and x2 equals lambda y2, for some number lambda greater than or equal to 0, then equality holds in the Schwarz inequality. Right? And prove the same thing if y1 equals y2 equals 0. And then now suppose y1 and y2 are not both 0. And that there is no number lambda such that, the other condition holds, such that xi equals lambda yi. Then we have that 0 is less than minus okay, using using the one that we just did, problem 18. Complete the proof of the Schwarz inequality. Whew. All right, there's a lot of writing in this one. Okay, so we want to use problem 18 to complete the proof of the Schwarz inequality. So we can, I mean, you could check that this works. You just multiply everything out and you'll see that it simplifies to give you the right-hand side here. The fact that this is always greater than 0 follows from that important fact that we talked about a second ago, that a squared is always positive, right? So a squared plus plus b squared will always be positive if they're non-zero real numbers. All right, so if you look here, we have a quadratic equation. Whoops. Sorry, we have a quadratic expression in the variable lambda. So that means, so by, I guess here's the proof. By 118, this inequality, the fact that it's greater than 0, should I write it over? Hopefully you guys know what I'm talking about. This inequality, right? This polynomial is always greater than 0. By problem 118, I'm not going to rewrite this whole thing over. Is true, implies so by 118, then that means that what's the value for b? It's so b in this case would be negative 2 x1 y1 plus x2 y2. A would be y1 squared plus y2 squared, and c would be x2 squared plus x1 squared. Or even more simply, I can just divide, factor out by a. Let me do this on the next page. So we have something that looks like this. I'll use the a's instead of those things just because it takes forever to write it. Whoops, it should be lambda. Or actually, let me do it up here so I can save some room. Then a lambda squared plus b lambda plus c is the same thing as a lambda squared plus b over a, b over a lambda plus c over a is greater than 0. Okay, and we're assuming that at least one of the y1 or y2 is not 0, so we can divide out by a, which implies that lambda squared plus b over a lambda plus c over a greater than 0, since a is not 0. All right, so that if this is greater than 0 from problem 118, then we know that this implies that b over a squared minus 4, c over a is less than 0, which implies b squared over a squared less than 4, c over a, b squared less than 4 ac when you simplify. Okay, and b squared was right over here, that was 2 times x1 y1 plus x2, y2 squared less than 4. A was y1 squared plus y2 squared. And C was x1 squared plus x2 squared. Right, and if you simplify the left-hand side, when you square the 2, you get a 4. We can divide out by the 4s, and if you take the square roots of both sides, you get what you want. All right, so that's the proof of that statement. And also they asked us also in the case where x1 is lambda y1, x2 is lambda y2, and also in the case where y1 equals y2 equals 0, show that equality holds. I won't actually do that here just because it's very simple. You just plug those things into the formula here and you'll see that you get equality. So you can check that yourself. I'm not going to bother doing that. You just plug it in, right? So that's part, what was that, part A, I think? Okay, part B says prove the Schwarz inequality by using with xi equal sorry, with x equal xi over square root x1 squared plus x2 squared, and y equal yi over square root x1, sorry, y1 squared plus y2 squared. Oh, that's my phone. Hang on 1 second. Sorry about that, guys. I'm just going to put this on silent for a minute. Okay, for I equals 1 and 2. Okay, first off, maybe I should say where this comes from. This comes from the fact that for if x and y are any real numbers, so maybe I'll just write this as a note. X and y are real numbers, then x plus y squared greater than equal to 0 by that fact, that important fact that we said a few minutes ago. And if you expand this and sorry, this should be a minus y. Minus y. If you expand this, you get x squared minus 2xy plus y squared greater than equal 0. And then you just add 2xy to both sides, and that gives you that expression there. So let's do the proof. All right, so if we plug x and y into the above formula, then we get, I'll do it in general for both. So 2xy would be 2xi yi over square root x1 squared plus, plus x2 squared. Y1 squared plus y2 squared. All right, for I1 or 2. And if I add the two things together, then we get 2x1 y1 plus x2 y2 plus x2 squared. Let me just fix that. Square root y1 squared plus y2 squared is less than or equal to x1 squared plus x2 squared over x1 squared plus x2 squared. Once you rearrange everything, plus y1 squared, y2 squared. Which is equal to 2. Okay. And then you can multiply both sides by the square root signs. And actually, let's just so I don't have to write the 2's. You can divide out by 2 here. That gives you 1 when you do that. All right, so that shows the Cauchy-Schwarz holds. Part C. All right, what does that say? Prove the prove the Schwarz inequality by first proving that is equal to Okay, by first proving that. Okay, and this just follows basically by just multiplying everything out. So proof. If you multiply out the left-hand side, maybe let me write it like this just so I don't have to write the whole thing out. So left-hand side, when you multiply it out, gives you x1 squared y1 squared. And right-hand side, when you multiply that out, you get two middle terms that both have, for the first term there that's being squared, you get two terms that have a factor of x1, y1, x2, y2. So I'll just write it as 2 times that. Right, and then for the second part, when you square that, you get a negative 2x1, x2, y1, y2 plus x2 squared, y2 squared. Right, and here notice that these cancel out, and these two things are equal. Right, that's really all it is. And then the Cauchy-Schwarz follows directly from the fact then that since this thing oops, that's a 2. Since this thing is equal to this thing, this is greater than or equal to that, since x1 y2 minus x2 y1 squared is greater than or equal to 0. All right, so Cauchy, and then just take the square roots of both sides and you get the Cauchy-Schwarz inequality. So that's the proof. All right, part D says deduce from each of these three proofs that equality holds only when y1 equals y2 equals 0, or when there's a number lambda greater than or equal to 0 such that x1 is lambda y1 and x2 is lambda y2. Right. I guess maybe we can just actually just go back through the proofs to just see where those things, where that follows from. We already know that it works. The Cauchy-Schwarz is satisfied if those things are true. Again, you could just see that by plugging. Where am I? Where's Cauchy-Schwarz? Here. Not A, sorry. All the way back here. If you just plug, like if y1 equals y2 equals 0, it's clear that you get 0 less than or equal to 0, which is true, right? That's if y1 equals y2 equals 0. And same thing if x1 is lambda y1 and so on, you'll see that you get the same thing on both sides. So we already know that. So now he's asking us to check the reverse thing. So in the first proof, what did we use here? We used this fact over here to prove that, and clearly that's true only in the case. Sorry, this would be this 0 here. Whoops, over here. Sorry, over here. This inequality sign would turn into an equal sign if x1 it was equal to lambda y1, right? Because these two things would be equal, so you would get 0 squared, and same thing here, you would get 0 squared. So this, instead of being an inequality, you would get equality. So that would be equal to 0 in that case. And the case where y1 equals y2 equals 0, again, that should you should just plug it in, you'll see that it works. So that's for that one. And the second proof, where did we do part B? Over here. This thing over here is greater than where did I write? Oh, over here in the note. So this thing is equal to 0 when x equals y, meaning where x. So if x is equal to y, then that means that these things are true. Oops, y1 squared plus y2 squared, which means that xi, remember I can be 1 or 2 here, would be equal to square root x1 squared plus y2 squared, or square root y1 squared plus y2 squared yi. So in this case, lambda would be this. X2 squared. All right, so that takes care of that proof. And then what was the last one? Part C. This thing. So if you look at how we did this proof, we relied on this fact here, right? But this would be equal. So we would get the equal if this thing was equal to 0, right? Meaning that x1 y2 minus x2 y1 was 0. So actually, let me, just because I don't have space, in part C, equality means x1, y2 minus x2, y1 would have to be 0. And that would mean that x1 is x2 over x1, y1. And actually, x2 would be the same thing as x2 over, oh, should this be, hang on, this should be y2 here. I'm trying to solve this in my head. X1 would be x2, y1 over y2. Sorry, this should be y2 here. And this would be x2 over y2, y2, because the y2's just cancel, right? So in this case, lambda would be x2 over y2. So that follows from that. And again, the y1 equals y2 equals 0. I'll skip that just because it's easy. So that's part D. And I think that's the last part to number 19 here. That's the last part to number 19. I think that's all the ones I needed to do. Let me just double check in chapter 1, just so I'm not skipping anything. Okay, so that's chapter 1, and we're already a long way into the video, so I might not get very far into the chapter 2 problems, but let's do a couple of them at least, and then we'll save the rest of them for the next video. Like I said, I don't want to burn everybody out by too long a video. So let's move on to chapter 2 then, and we'll start with question number 3, which is not one of the ones that he recommends to do in the chapter, but you do need a result from problem 3 to do one of the problems later on. So, and I'm not going to do all of the parts of problem 3, just because we don't need all of the parts to it. We just need 2 particular results from question 2. So I'm going to do part A and I think it's part A and part C. Part A and part D. So I'm going to skip the other parts to question number 3. Again, just to keep the time a little bit down here. So in part A, and just bear with me, I'm going to copy the question down from the chapter. Oh, actually, this definition we need before I get to part A. Let me just write down the definition. Okay, if 0 is less than or equal to k, is less than or equal to n, the binomial coefficient n choose k is defined by n factorial over k factorial over n minus k factorial. If k is not 0, and n choose 0 is the same thing as n choose n is defined to be 1. And in all of the cases, if k is less than 0 or k is greater than n, n choose k will define to be 0. Right? And in part A, they want us to prove an identity involving binomial coefficients. So prove that n choose k is equal to n minus 1, k minus 1, plus n minus 1 k, choose k. All right, which is oh, I'm sorry, this should be n plus 1 here, sorry. I want to write it the way that he has it in the book here. N plus 1, n k minus 1, plus n k. This identity yields Pascal's triangle, if you remember from high school algebra. So I'll just make a note about that. Note this identity yields Pascal's triangle. All right, so let's actually go to the next page and prove this, which we'll do just by using the definition. So proof. So if we look at n, k, choose k minus 1, plus n choose k, then by the definition, this is n factorial divided by k minus 1 factorial times n minus k plus 1 factorial plus n factorial over k factorial n minus k factorial. And if I factor out common factors, the greatest common factor from both of the terms, that's the GCF, and we're left with 1 over n minus k plus 1 plus 1 over k, which we can put over the LCD to combine them. N factorial, k minus 1 factorial, n minus k factorial. This is k plus n minus k plus 1 over k, n minus k plus 1 times k. And notice the k's here cancel. Which is n factorial. Maybe I'll just write it next to it. So notice that we get, this simplifies to give you n plus 1. So you have n plus 1, n factorial times n plus 1. And in the bottom, we have k times k minus 1 factorial. And we have n minus, we could write n minus k plus 1 as n plus 1 minus k. Times n minus k factorial. Which is the same thing as n plus 1 factorial divided by k factorial times n plus 1 minus k factorial, which is the same thing as n plus 1. Choose k factorial, choose k, and that proves the identity. Okay, going on then to part B, they want us to prove the binomial theorem, which says, this is part, where do I say? Part D. I'm sorry, this is not part B. This is question 3, part D. Which says, prove the binomial theorem. Right, which says if A and B are any numbers, and n is a natural number, then a plus b to the n is a to the n plus n, choose 1, a to the n minus 1, b plus n 2, choose 2, a n minus 2, b squared plus dot 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 n, choose n minus 1, a b n minus 1 plus b to the n. All right, that's what the binomial theorem says. So we want to prove that, and we'll do it by induction on n. So induct on n. Base step. A plus b to the first power is equal to 1 times a plus 1 times b, which is the same thing as 1 choose 0a plus 1 choose 1b. So that checks out. Inductive step. Start with the inductive hypothesis. So assume, I'll just say assume binomial theorem holds for some natural number n, just so I don't have to write that long string of things out. Okay, and then consider n plus 1, which I'll have to do on the next page. Consider a plus b to the n plus 1. That's equal to a plus b times a plus b to the n, which is the same thing as a plus b times a to the n plus n, choose 1, a to the n minus 1 b plus dot 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 plus n minus 1 a b to the n minus 1 plus b to the n. That just follows by inductive hypothesis. And then we can distribute the a plus b using the distributive law, which is equal to a to the n plus 1 plus n, choose 1, a to the n b plus dot dot dot, and choose n minus 1, a squared bn minus 1 plus abn plus a to the n b plus n choose 1, a to the n minus 1b squared plus n, whoops, plus dot 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 plus n choose n minus 1, a b to the n. Sorry, my fingers are falling asleep. Plus b to the n plus 1. And if I regroup things in a convenient way, here I have a to the n plus 1. All right, let's see, a to the n b, I have like terms here and here. And the coefficient here is 1, right? Which is the same thing as n choose 0 plus n choose 1 times a to the n b plus, let's see, what's next? We would get n times n minus, let me do the dot 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 here. Dot 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 plus a squared bn minus 1 to the n plus 1. If I fill in some more of the terms, it might be more obvious, but should we do the a b to the n? Minus 2. I think we would end up with, let me just see what I wrote down here. I'm trying to save space with not writing out more terms, but this will be n choose n minus 1 plus n choose n a b to the n plus b to the n, whoops, this should be in parentheses, plus b to the n plus 1. If you notice, this ends up being a to the n plus 1. And then by part A, this would be, what would be n plus 1 choose 1 times a to the n b plus dot dot dot. This would be n plus 1 choose n a b to the n plus b to the n plus 1. So we're using that identity from part 1. So by part, or part A, I think, right? Part A, right? Which it gives you the same thing as what the binomial theorem would say. So that gives you the binomial theorem. All right, so that follows from mathematical induction. There are other parts to question 3. Like I said, I'm going to skip those just for time. I'm already feeling like this video is getting too long. Maybe I can squeeze one or two more in if they're short. That was number 3. Next one I wanted to do was actually number 6. You see 6, 7. Ugh. The next one I want to do is number 6, and there's a bunch of parts to that too. How many pages do I have left on here before it's a double back? 18. Let's do number 6, and then I'll start with number 7 next time. I think that probably makes the most sense. So I'll do one more in this video, and then in part 2, we'll continue with question number 7, which relies on question number 6. So this is 2.6. All right, let me copy the parts here. Okay, so number 1 says, so should I show you there's like a whole paragraph before part 1, where he derives a formula for the sum of the first n integers squared. Yeah, I should probably write it just because in case people don't have the book. Okay, so the formula for formula for this follows from the formula okay by you can derive this for k 1 through n. So if you look at 2 cubed minus 1 cubed, uh, 3 cubed minus 2 cubed, whoops, cubed minus 2 cubed. You can keep going on until n plus 1 cubed minus n cubed gives you so if you add all these things up on the left hand side, you'll notice that all the middle terms cancel out, so you end up with right, you're adding 1 to itself n times. So that gives you a formula in term for 1 squared plus 2 squared up to n squared. If you know a formula for the sum of the first n integers, which we do, and 1 plus itself n times is n. So let me just continue this on, on the next page. So that means n plus 1 cubed minus 1 is equal to 3 times the sum of the first k squares plus 3 times the sum of the first k integers, first n, the sum of the first n integers, sorry, plus n. We actually already know a formula for the sum of the first k integers. We derived that in the chapter, right? So this would be n plus 1 cubed minus 1 plus 3 summation k squared plus this would be 3 times n plus n times n plus 1 . Right, and we can solve that for the sum of the first k squared. So for the first n squares, k equals 1 to n. Okay, so we could solve that for this summation, and that would, once you simplify, that'll give you a formula for the sum of the first k, the first n squared in natural numbers. And there's a few problems here that are like this, where he wants to use this same idea. So in part A, or part 1 rather, he wants us to derive a formula for the sum of the first n cubes. Right, we could use a similar idea. We can use a formula similar to the one that he had, but for cubes. In other words, k plus 1 cubed minus k cubed. I'm sorry, to the fourth power. We want 1 power higher. Right, that's equal to what is it? 4k cubed plus 6k squared plus 4k plus 1. That follows by the binomial theorem. Right, the one that we we just did. Feels like a couple hours ago already. Okay, so this formula follows, and you can do a similar thing. For example, 2 to the fourth minus 1 to the fourth is 4 times 1 cubed plus 6 times 1 squared plus 4 times 1 plus 1, 3 to the 4 minus 2 to the 4 is 4 times 2 squared. I'm sorry, 2 cubed. 6 times 2 squared. 4 times 2 plus 1. And again, you can just keep going on until you get to n plus 1 cubed minus n. Sorry, n plus 1 to the 4 minus n to the 4 is 4 n cubed plus 6n squared plus 4n plus 1. Right, and when you add all those things together, you get n plus 1 to the 4 minus 1 equals 4 times the sum of the first n cubes plus 6 sum first n squares plus 4 times that plus n. And we know a formula for this, we know a formula for this by things we've already done. So you could solve for k cubed as a polynomial and by bringing everything to the left-hand side and solving for the sum of the k cubed. And so that gives you a formula in terms of the n's for the sum of the first n cubes. The next problem, actually, I'm gonna have to go back to the beginning here. I'm not going to do, there's 4 parts to this. I'm not going to do all of them. They're very similar. So maybe that was part 1. You can prove that formula using induction, but I'll just derive the formulas. Part B is very similar, except he wants you to find a formula for the sum of the first n fourth powers. So you would do a similar thing for part 3. He wants you to derive a formula for this. What is it? 1 over 1 times 2 plus 1 over 2 times 3 all the way up to 1 over n times n minus 1. Or n plus 1, rather. He wants you to derive a formula for that, which you can do if you know the fact that 1 over n plus 1 minus 1 over n is always equal to sorry, it would be the other way around. 1 over n minus 1 over n plus 1 is equal to 1 over n times n plus 1. For any natural number n. And if you do a similar process, like, you take 1/2 minus 1 over 3, you get 1 over 1 plus 2, and so on like that. You just keep going. You'll find that you get a formula 1 over, sorry, you get 1 minus 1 over n plus 1. You'll see is equal to 1 over 1 times 2 plus all the way up to 1 over n times n plus 1. And you can prove that works for any natural number n by using induction. I'm going to skip over that because I'm starting to get actually kind of tired, and it's relatively straightforward, the proofs by induction for that. And we're going to use this question, something similar to the process that we did here for question number 6 to do question number 7. But again, I feel like this video is already too long, so I'm going to stop this one here, and we'll start with number 7 in the next video. All right, guys, I hope this wasn't too long for you. But we'll continue with the questions from chapter 2 in the next video. So I'll see you guys in that one.